lemniscate and cardioid. All right, so let's look up lemniscate.
It's basically, when you're looking at the picture, it's essentially you have an hourglass with some spacing in between it, and consider if you had something straight like a meter stick, and how could you transition from touching all the points on one to that balance point where you're literally having a handoff to the other sheet.
Yes, yes. And the red dot is in the middle of the line, and it moves around as we just wrap this line, right? It's being touched and rolled, and when it hits the other side, then we roll it this way.
It's being
and we just keep rolling back and forth.
Being completely traced out by the lemniscate, or what we colloquially refer to as an infinity side or a sideways eight.
Yeah. So they call this the pedal curve of the rectangular hyperbola. Or you can think of this as the inverse transform of the hyperbola.
Or figure eight.
Yeah, or figure eight. But the thing I really want to have us notice right now is that it is an inversion of the hyperbola.
Right.
It's, in fact, in this picture you see it really well. It's what you would expect to find inside the hyperbola. Okay. Now, what about the cardioid? Does it relate to anything in this kind of geometry?
Oh, I love it. Yep. When you have, was it an equidistant circle tracing out on the outer boundary of another circle, after it goes a full 360 degrees around the inner circle, it will touch again.
So anything that fibers into a bunch of strands. The strands will move around each other like circles, right? But that tendency to wrap around each other would form this shape. No matter what, any two circles of same size rolling around each other trace out that shape if you pick one.
Utilizing one single point. Yep. Okay.
Okay, but what do we want to think of this curve as? That path that follows, what kind of path is it? Well, it's the inverse curve of the parabola.
Oh.
It's literally the inverse curve of the parabola with the focus at the center of inversion. Okay, so now we have inverses of hyperbolas and inverses of parabolas, and this is the shape that makes hyperbolas and parabolas. So what's the inside going to look like that's holding this shape together? It's going to be made up of
hyperbolas and cardioids.
Or lemniscates and cardioids.
Lemniscates and cardioids.
Inversions of those two kinds of shapes.
Oh, that was all the picture. Okay, got it.
Now, I told you there was going to be a really cool connection to the Mandelbrot set. What's the predominant shape of the Mandelbrot set?
Cardioid.
Cardioid.
Oh.
What's some of the features? So we'll pull up a picture of the Mandelbrot set. Let's look at some of the outstanding features really quick that you might want explanation for.
The Mandelbrot says a set of complex numbers C for which the function f sub c of z equals z squared plus c does not diverge to infinity when iterated from z to 0. When you start to zoom in to this, apparently it really just depends on your resolution. It keeps going.
It keeps going in, but the limits out are +2 and -2. The picture that the spike doesn't keep going forever this way. The more you zoom in, it limits it. -2 and +2, the whole picture. That's one thing to note. So at 2 and -2, that's just double 1 and -1. We really care about our unit circles. Kind of interesting. This is a bifurcation structure. We're thinking. Okay.
Yeah.
So 2 would be an important number, but there's this spike way out here.
Yeah.
Let's click on the picture.
Okay.
Other than the main feature being that we have a cardioid, which we form by rolling one ball around another.
Yeah.
We also have that sized ball sitting outside of it next to it. So one ball rolls around another, and then we have the size of the ball that does the rolling right there.
Yeah.
And then this thing does itself repeating shape, but it ends up making this next big, this let's call it a vertex.
Okay.
Okay, let's think of that in the general shape as a vertex
of
the picture. Think of this now. We have a circle I'll put in between these bounds. And the inversion of the circle, meaning you're using circle inversion to cross from inside and outside the circle like it's a mirror, that blue part maps to this blue part. This red part maps to that, this green part maps to that green part, right? So that's what we mean by inversion. And if you let the circle go all the way to touch, then these will touch too.
Yeah.
So that's what we really want, the touching ones. But now, I'm going to assert this, that in between these boundaries we have a lemniscate maintain the inversion curve, and we have 2 of these cardioids. Why? Well, we put one cardioid in here,
right?
And if we put in a second cardioid there, and then we say, wait a second, my favorite cardioid is the Mandelbrot set. Let's scale it to match perfectly right there now to fit inside of our hyperbolic construction. What does it look like?
Oh.
That vertex becomes the focus of this
the
side.
other one.
So you throw in this one, and both of those focuses now have internal constructive balance. You see what I mean? Symmetry happening here. So there's a lot more to say, of course. This is leading and just a start of the conversation. But the point is, we're noticing we can think of the internal construction of hyperbolic geometry itself as being maintained under these two kinds of balances, right?
Yeah.
And therefore, since we thought it was the trivial fractal to begin with on the charge boundary, we're going to be looking at this constructive, literally the prime constructive anyway. We're already thinking that this is the prime geometry. So all the prime numbers are contained in this sequence, all in fantastic ways.
Well, this is the beautiful thing. And I remember you had quickly showed me that the other day. I created a connection, and now I didn't actually realize that was exactly what it meant. I'm like, okay, we're kind of lining up, but it really does look like if this fascinating fractal that has all these properties and it's freaking beautiful. I just stared at it for the past minute of it, zooming in further down on the page, but you literally have this joined with this. You have your central balance point, and at that point, I don't know if we could map out the actual transition from that to that. If it is perfectly balanced, maybe it could
Think
have.
about inside our hyperbolic figure eight knot. We're saying that the first balance that's made is a two-dimensional circle, and outside that there's going to be then 6 other things expressing that circle. Right? Making our next scaled balance.
Mm-hmm.
When you see this shape, you know it takes 2 circles of the same size to make. Right?
Okay.
And there's a third one right there. So this picture's got like 3 circles making it, right? 3 same size circles making it. 1, 2, 3. The other one would have 3, 4, 5, 6 in the balance.
Because of the size difference.
Yeah, the 3 circles constructing that one, the 3 circles constructing the other one, right? And over this middle is where our
for them coming to
yeah. That's what I'm seeing. I'm seeing that this shape is composed of 3 identical sized circles.
Well,
our shape decomposes into 6 identical sized circles outside here. So 2 of the shapes is the decomposition structure of that fractal geometry. We're assuming a hyperbolic geometry. So this might be kind of the end of where I was going to go.
Okay.
But yeah, it is. I just wanted to bring us to this beautiful connection between the Mandelbrot set, which a lot of people spent some time developing intuition over, or at least appreciating.
It's fascinating. I've stared at that thing for a while.
And the story of hyperbolic geometry. That's the connection we're really trying to point out here, that we have a natural connection between the hyperbolic space-time, four-dimensional hyperbolic space-time construction that Einstein revealed, right? A natural story between that and the internal shapes being cardioids and lemniscates. Oh, lemniscate, one more thing I can say about lemniscates. Cool. Maybe be an introduction. So the lemniscate that we really care about here is going to be the one that goes out to 1. I made a mistake about this earlier, so it's good to do it correctly. It goes out to 1, and it's like a circle, but it has to go through its own center, or like an ellipse, but it has to go through its own center instead of the cross. So this is the lemniscate of Bernoulli, the unitary lemniscate. Okay. Its length is what? This length is 1. What's the length of that curve? There's got to be an exact number, and it might be useful. Like, is it pi? Is it 2 pi? Is it anything related to pi? What is that number? Well, it's represented as S. The whole length of this lemniscate is S. So arc length of the lemniscate. Okay, S isn't the lemniscate constant. It's the whole arc length of the lemniscate. The lemniscate constant equals S over 2, which means it's the arc length of just one petal. That's kind of a unique number in here anyway. And also, you'd think that one would too, because it's divided up exactly in these balances. So, turns out L1 equals L over 2, which is S over 4. So yeah, we have 3 of the lemniscate constants now are just easily seen here. S is all of that. L is just this or just this. L over 2, or sorry, L1 is L over 2, and that's just 1/4 of the whole path, or 1/2 of one petal.
Right.
Great. So that's the lemniscate constant there. I didn't give you the digits. So this is how we represent it, like we represent pi with a letter. All right. One interesting thing that might connect to everybody who took any training with cosines and sines.
I remember I got taught it, and I just didn't see any. I got very bored and doodled in my notebook.
Here, if we start at 1 and we do sine or cosine, it doesn't matter. We go up to 1, goes down to -1, back to there. Right? Sine wave, traditional unitary. Which we touch in there. -1. This is the unitary sine or cosine wave length, and it just shifts if it's sine or cosine, right? So the value here is 2 pi. When this is 1, this is 2 pi. So this single, most familiar wave decomposes into units of 1 and 2 pi. We have scales we care about, 1 and 2 pi. Great. What else is in this unitary sine wave, unitary cosine wave?
Oh.
An arc length.
Yeah.
This length from here, put the rope and drop the rope here and figure out how long is this path. This straight path is 2 pi. This straight path is 1 and this one's -1, so total is 2.
Right.
Okay, but this wiggled path has a different length. It has a specific length to the unitary cosine sine wave that we're all used to using. What is it? Well, that length right there is equal to, we'll call it the length of this sine wave, or length of the cosine wave, they're equal. That arc length is going to be 4 pi divided by s plus s. S is the arc length of the lemniscate. The circle divides up into the cosine and sine. The sine and cosine divide the sphere using lemniscates.
That's fascinating. Why?
Because they're back and forth,
Because it's twisting and it's, okay, it just happens to come out to be that ratio.
Yep, back and forth, inside out. Okay, so there's a connection. If you've never had a direct mathematical connection, how to see why would I care about this constant or this constant or that constant? Well, if you got to the point where you've seen how we decompose circles into sines and cosines, well, sines and cosines both have this magical number fixed into their unitary wavelength expression. There it is. It takes us right to arc length of the lemniscate.
I think the first time I ever heard that was during some of the Wolfram Physics Projects live streams. I remember Jonathan Garrod, shout out to Jonathan, he'd been mentioning that, and I'm like, I didn't even know what that was. I was already looking up so many different things, and just even the past couple of days, it's just, there's so much out there. It's not one person can know everything, so it's like the ability to write it down and have access to that information. I think that's a total game changer.
Yeah. This is beautiful, isn't it? Basic geometry's telling us stories now.
I feel also some of the history and kind of how we got there too helps put a specific context to figure out, it's like, how did we actually get to this? Because actually going through the process, if we know what people did before, we can refine the process.
That's what we're trying to do, is keep making more and more sense of this, get more and more clarity about the primes, about all the questions you could ask about the primes, or about hyperbolic geometry, or about physics or chemistry or biology. Yeah, it's the process, though.
Well, and that's the thing. I look at some of these things, and there are a lot of really talented people out there, and I've had the benefit of interacting with a number of them. And if there's anybody out there that has a particular set of skills, and they really feel like this is something they would like to investigate for themselves, let us know. I think it'd be pretty cool.
Yep. All right. Cool.
Sweet.
Till the next conference.
Absolutely.
Or the next video.